Welcome to the debate. Right now, there is a quantized model sitting on a solo developer's MacBook that can actually outperform the multi-million-dollar supercomputers of, just 2 years ago.
It is pretty wild.
It is, but the companies building massive hyperscale cloud infrastructure, they want you to think local AI is just a toy, like a novelty that can't handle real enterprise workloads. So are we headed for a centralized AI monopoly governed by a few API endpoints, or a decentralized developer rebellion built on sovereign silicon?
I mean, it really is the ultimate architectural question for anyone writing software today. Do you tether your entire application to a corporate cloud, or do you run the weights locally? And to understand where we are, you really have to look at where we've been. You remember what happened in 1999 when the GeForce 256 dropped?
Oh, absolutely. It fundamentally changed the trajectory of computing.
Right.
NVIDIA marketed it as the world's first true GPU. And what it did was take the burden of transform and lighting, the heavy mathematical lifting of 3D rendering, away from the CPU. It centralized that specific, highly parallel workload onto a discrete piece of silicon.
It formalized the graphics pipeline in hardware.
Yes! It was an industry-wide acknowledgement that certain mathematical workloads demand centralized, dedicated infrastructure. You can't just abstract them away to general-purpose hardware.
You suddenly had a hard, physical boundary between general-purpose computing and specialized parallel processing.
Exactly. And today, system architects are standing at an almost identical crossroads, just on a macro scale. I look at the physical constraints of large language models, and I have to conclude that the inflexible mathematics of neuroscaling laws and just raw compute requirements make centralized, massive-scale cloud infrastructure the absolute only viable path for frontier AI.
I come at it from a completely different direction.
Go on.
Because that centralized paradigm, the big tech paradigm, is built on a brute force data harvesting monopoly that solo builders are actually already circumventing. We are seeing the rise of a highly capable, off-grid ecosystem.
Capable, sure. But
highly capable, algorithmic efficiency, post-training quantization, and open-weight models are, well, they're democratizing AI. Developers can build sovereign systems right now without paying the cloud tax, and more importantly, without sacrificing their users' proprietary data to a centralized black box.
look, I understand the appeal of that decentralized vision, but let's talk about the hard math. Anyone building an application right now might be thinking, why do I care about parameter scaling if I just want my app to parse some text?
Right, that's the common question.
Here's why. It comes down to the chinchilla scaling laws. These aren't just academic suggestions, they are an inescapable physical reality of AI development. The cost of training an optimal model, what we call C, is dictated entirely by the size of the neural network, N, and the size of the training data set, D.
Yeah.
The math tells us that it takes 6 FLOPS, floating point operations, per parameter just to train on a single token.
Which, is a staggering amount of compute.
It is a massive financial and hardware gravity well. Look at the historical data. Training PaLM, a 540 billion parameter model, cost $8 million. Megatron Turing NLG 530B cost around $11 million.
And that's just pre-training.
Exactly. That is just for the pre-training phase before you even get to fine-tuning. This isn't just an expensive compute bill, it's an economic moat. It means the frontier of AI is governed by CapEx, not just code. We are moving from a software era where 2 kids in a garage could build a search engine to a heavy industry era where you need the equivalent of a digital oil rig just to play the game.
But see, you're assuming that the only way to get intelligence is to build a digital oil rig.
Because research clearly shows that advanced capabilities like complex chain-of-thought reasoning, decoding spatial words, or executing multi-step logic, they only reliably activate or emerge in models that scale beyond 62 billion parameters.
What? But
if you want emergent reasoning, you need scale. To run a forward pass on models of that size, let alone train them, requires massive data center interconnects. You need thousands of Tensor Core GPUs communicating over NVLink. And you need a memory bandwidth that local silicon simply cannot ever match. The compute gravity pulls everything to the center.
I hear you, but the architectural bottleneck is shifting, and the brute force method just isn't the only way anymore. We are no longer living in an era where you need a dense, trillion-parameter model to achieve state-of-the-art results.
Are we not?
No. Look at DeepSeek R1. This is a 671 billion parameter open-weight model that achieves reasoning capabilities comparable to the best proprietary models, but at an absolute fraction of the operational cost. And it does this by utilizing pure reinforcement learning rather than relying on massive, scraped human datasets.
Wait, but 671 billion parameters is still massive. You can't fit that on the local workstation.
You can't fit the whole thing if it's active all at once, sure. But the architecture is completely different. It relies on a mixture of experts, or MOE. Think of it like a massive hospital.
Okay.
You don't see every single specialist when you walk in the door, right? A triage nurse routes you to the exact doctor you need. MOE uses a gating mechanism that routes each input token to specialized neural networks. So during inference, you are only activating a small fraction of those parameters, maybe 37 billion active parameters per token.
Which is more manageable, yes, I'll give you that.
Exactly. And when you combine MOE with post-training quantization, the game changes entirely. Quantization is where we take those massive 16-bit floating point parameters and truncate them down to 4-bit or 8-bit precision.
Right, you're chopping off the decimals.
Basically, you are literally compressing the physical memory footprint of the model, and suddenly you can fit incredibly capable, sovereign AI into consumer VRAM. Developers are running these models locally today. They are bypassing the API bottlenecks, maintaining total data sovereignty, and completely avoiding that cloud tax.
I have to push back on this idea of a local utopia, though. The math just doesn't support it when you look at generalization. Yes, mixture of experts and quantization are impressive engineering optimizations. I won't deny that.
Thank you.
But they do not negate the fundamental law of GPU evolution, which has always favored raw compute scaling and memory bandwidth. When you quantize a model, you are inherently losing precision. You're dropping from highly detailed 16-bit representations down to blocky integers.
Yeah, but we recover a lot of that with dynamic quantization codebooks.
You recover some of it, sure. But a localized compressed model fundamentally cannot generalize across domains without the massive pre-training that only occurs in a data center. A 4-bit quantized model is just a low-resolution shadow of the original network.
I wouldn't call it a shadow.
It is. It might be fine for a highly specific coding task, but it lacks the broad, emergent reasoning of the uncompressed base model.
But quantization isn't happening in a vacuum. You're assuming that every solo developer needs a generalized model that knows the capital of France, how to write Python, and how to write a sonnet.
Most enterprise apps need flexibility.
They don't need all of that at once. The battle has moved to fine-tuning. If a developer squashes a model down to 4-bit and loses some resolution, the natural next step to recover that accuracy for their specific use case is fine-tuning, specifically via LoRa, or low-rank adaptation.
Right, but fine-tuning still requires moving gradients around. It requires compute.
A microscopic fraction of the compute. Instead of updating all 70 billion parameters, which, as you pointed out, takes a supercomputer, LoRa freezes the original model weights. It only trains a small set of injected low-rank matrices.
Okay, explain that for someone visualizing it.
Think of a massive spreadsheet with millions of rows and columns. Most of that information is mathematically redundant. LoRa decomposes those massive weight updates into tiny, dense matrices. It's like taking a huge, high-resolution image and only saving the exact pixels you want to change. You get 90% of the accuracy for 1% of the compute cost.
But where do they run it? You still need VRAM to hold the frozen weights and the gradients for the LoRa adapter. A standard consumer graphics card has maybe 16 or 24 gigabytes of VRAM. That is a hard physical ceiling.
See, that ceiling doesn't exist in the same way anymore. System architects are running this on local machines equipped with Unified Memory Architecture, or UMA.
Ah, like the Apple chips.
Exactly. Look at modern Apple Silicon, or APUs from AMD. In a UMA setup, the CPU and the GPU don't have separate memory pools. They share the exact same pool of system RAM. So we aren't bound by that 24 gigabyte limit.
You just allocate it dynamically.
Right. A developer can allocate 64 or 128 gigabytes of fast system memory directly to the GPU block. And if that isn't enough, we are seeing external GPUs, eGPUs connected over incredibly fast Thunderbolt or Oculink ports, pushing up to 40 gigabytes per second. The hardware to run these parallel workloads isn't locked in a server farm. It's literally sitting on the developer's desk.
Okay, I see the appeal of the hardware setup, but let me give you a different perspective on the data itself, because all of this hardware talk ignores the data wall.
The data wall?
Yes. You mentioned sovereignty earlier, which is a noble goal. But the reality is that robust foundation models are inherently reliant on massive data pipelines that solo developers simply can't replicate.
And we should be thankful they can't replicate them, because big tech's data pipelines operate like a DDoS attack on the entire internet.
That's a bit hyperbolic.
It's really not. They deploy AI web crawlers that systematically ignore robots.txt files, completely bypassing standard methods used by site owners to block web scrapers. They are vacuuming up the entire web, and it has resulted in massive legal fallout.
Right, the copyright issues.
Yes! Just recently we saw Anthropic reach a preliminary $1.5 billion settlement with authors because they stored millions of pirated books for model training. The corporate data wall isn't just a technical moat, it is a massive legal and ethical liability.
That is a legal challenge they are navigating, yes. But
It's a structural flaw for developers. If you are building enterprise software right now, you cannot send proprietary corporate data or sensitive user information to a centralized API that might just use it to train its next iteration. Building local retrieval augmented generation, or RAG, is the absolute only way to ensure data privacy. True sovereign AI means local execution, full stop.
well, I'm not convinced by that line of reasoning, because you are entirely discounting the security and safety infrastructure that centralized cloud providers offer. When you pull a model off the grid and run it locally, you are bypassing massive layers of reinforcement learning from human feedback, red teaming, and dynamic content filtering.
Some developers would call that bypassing censorship.
And system architects call it liability management. Let's look at the actual material threats in the wild right now. Without centralized oversight, local agentic models are highly vulnerable to prompt injection attacks, where malicious inputs completely override developer instructions.
Sure, prompt injection is an issue.
It's a huge issue. We've seen local models compromised by sleeper agents, hidden functionalities embedded in the open source weights that remain dormant until triggered by a specific tag in a user prompt. And worse, look at the recent phenomenon of LLM grooming.
Oh, the propaganda thing.
Right, the Pravda network, a pro-Russia propaganda aggregator systematically placed web content through mass publication specifically to bias the outputs of models scraping that data.
Which affects the big centralized models too, by the way.
Yes, but cloud providers have the massive compute budget and the dedicated teams to constantly audit, filter, and patch these vulnerabilities at the network layer. A solo developer running a quantized open-weight model on their desk cannot defend against state-sponsored data poisoning.
I think you're underestimating the open source community's ability to audit weights.
Let me offer an analogy from our hardware history that we started with. Think about the integrated graphics processors, the IGPs, from the early 2000s, the ones from SIS or VIA.
Right, yeah. You remember building rigs back then. They used UMA. They shared system memory, just like you were talking about with modern Apple Silicon.
Exactly. And they were fine for basic 2D tasks. If you wanted to run a lightweight workload, shared memory was great. But if a developer was rendering high-stress 3D graphics, they absolutely needed a dedicated, discrete GPU cluster.
They needed SLI.
They needed SLI, or NVLink, to draw images simultaneously across multiple GPUs. The exact same logic applies today. Local AI, quantized, and running on shared system memory is fine for basic text parsing or simple local RAG, but complex reasoning, multi-step logic, and secure, red-teamed enterprise deployment, that requires the discrete, centralized power of the cloud.
That's a really compelling historical analogy. I'll admit. But the analogy of 3D rendering breaks down here, because we are no longer just pushing static pixels through a pipeline. We are creating agentic loops. You have to consider that the entire battleground of AI has shifted from training optimization to inference optimization.
Explain exactly what you mean by that shift in this context. How does that solve the compute deficit for a local developer?
Well, the prevailing wisdom, which big tech loves to sell, was that to get smarter AI, you needed a bigger model. You had to scale up.
Right. The chinchilla laws.
Right. But inference optimization proves that you don't need a trillion-parameter cloud model to solve complex math or coding problems. You can use a smaller, local model and simply give it more time to think. We are seeing techniques like Monte Carlo tree search and chain-of-thought reflection being applied at inference time.
So instead of asking a massive model for an instant guess, you ask a small model to deliberate.
Exactly. Tools like OptiLM act as an optimizing inference proxy on your local machine. They apply best-of-n sampling, or a mixture of agents. The local model generates intermediate steps, evaluating its own logic, testing different paths, and scoring them before returning a final answer.
So it's checking its own work.
Yes! By shifting the computational resource away from the massive pre-training phase and into the local inference process, a developer can achieve state-of-the-art accuracy on their own hardware.
I acknowledge the brilliance of inference optimization. Using a local model as a rollout heuristic in a Monte Carlo tree search is an incredibly elegant software solution.
It really is.
But you're ignoring the thermodynamic reality of what happens to the hardware when you do that.
The thermodynamics? You mean the power draw?
I mean the physical power draw and the heat dissipation. The energy demands of LLMs are already staggering. A typical standard API query to a centralized model uses about 0.3 watt-hours.
Okay.
And that is just for a direct next token prediction. When you implement deep model native reasoning locally, where the system is generating long chains of thought, evaluating thousands of intermediate steps via tree search, and constantly context switching, the compute per query absolutely skyrockets.
It uses more power, yes, but it solves the problem without leaving the local network.
And it melts your rig.
Come on!
Seriously, you hit a strict thermal and power wall on local hardware. A high-performance local GPU can easily consume 300 to 400 watts. When local developers attempt to run continuous agentic reasoning loops, they saturate the memory bandwidth. The VRAM heats up, the system physically thermal throttles, clock speeds drop, and your tokens per second literally crawl to a halt.
That's a worst-case scenario.
It's physics. You simply cannot dissipate that much heat or supply that much power sustainably on a local workstation for continuous agentic operations. And this becomes even worse as we move toward multimodality, early fusion architectures that interleave high-dimensional image tokens, audio tokens, and text tokens simultaneously. That kind of sustained workload forces the heavy lifting right back into the highly efficient, liquid-cooled, optimized data centers of big tech.
I think you are severely underestimating the efficiency gains on the hardware side. Just as GPU designs are highly scalable, we are now seeing specialized AI accelerators, neural processing units, dedicated matrix cores, embedded directly into consumer silicon.
Yes, the NPUs.
Right. The performance per watt is increasing dramatically every single generation. But more importantly, the developer community is aggressively optimizing these systems specifically because they inherently distrust the centralized model.
You think the optimization is driven by spite?
I think it's driven by survival. When big tech changes an API endpoint overnight, or deprecates a model you built your whole app around, or worse, uses a developer's proprietary prompt data to train their next iteration, it breaks local workflows.
That is a fair complaint.
The drive towards sovereign AI isn't just about saving money on compute. It is about absolute control. By using small, highly quantized models running intelligent agentic loops, developers are building robust, private systems that do not depend on the whims of a centralized monopoly. They are proving that you don't need a massive data center to build incredibly capable software.
It is a fascinating tension, and it's clear the architecture is pulling in two very different directions right now.
Definitely.
If I were to summarize my perspective based on our discussion, I maintain that the inescapable physics of flops, memory bandwidth, and emergent scaling laws dictate a centralized future. The historical evolution of the GPU proves that as computational demands increase, the infrastructure naturally centralizes into specialized high-bandwidth clusters.
Right.
The complexities of multimodal processing, the immense thermodynamic demands of reasoning models, and the absolute necessity of dynamic security filtering against threats like prompt injection, all of that points to big tech data centers as the only viable, secure home for frontier AI.
Rapidly defeating brute force. The combination of open-weight models, post-training quantization, and unified memory architecture provides a highly efficient, capable path for solo builders.
Even with the thermal limits.
Even with the thermal limits, because by shifting the focus to inference time optimization, allowing smaller models to reason longer, rather than relying on massive parameter counts, developers can achieve incredible performance locally. This decentralized, sovereign path allows them to break free from cloud dependency, avoid the legal liabilities of corporate data harvesting, and maintain total control over their proprietary applications.
Despite our strong architectural disagreements on where the compute should physically live, I think there is a profound point of convergence in our reading of the material. The era of simply feeding larger and larger scraped data sets into next token predictors is ending.
Absolutely. We are hitting data exhaustion. The legal walls regarding web scraping are closing in, and the sheer volume of high-quality human text is basically tapped out.
Exactly, which means the entire industry is being forced to innovate on how models think through inference, reasoning, reflection, and agentic loops, rather than just relying on how much text they have read. The structural mechanics of AI are evolving from raw memorization to true algorithmic logic.
It is a massive paradigm shift, and ultimately, the direction this takes won't be decided by a debate between system architects. It will be decided by the developer community based on where they choose to build, compile, and deploy their code.
I completely agree. For those listening, I highly suggest exploring the source material further. Look specifically into the energy metrics we discussed, the thermodynamic constraints of local architectures, and the rigorous mathematical details of the chinchilla scaling laws. There's so much more to unpack regarding how these hard physical constraints shape our software possibilities.
It really is the defining engineering challenge of our time.
It truly is. We started this discussion by looking back at the GeForce 256, a chip that forced a hard boundary between general and specialized compute, effectively centralizing the graphics pipeline. Whether the AI pipeline remains locked behind the polished APIs of the cloud or shatters into a million local, sovereign instances running on developer desks, is a question that will redefine the internet itself. Thank you for listening.